Hey everybody, in this next video lesson, we're going to talk about pH and how to calculate pH. Now, in the last lesson, we talked about how water is at equilibrium and it produces concentrations of H plus and OH minus, and the higher the concentration of H plus, the more acidic it is, and the lower the concentration of H plus, the less acidic it is. But those molarities are such small numbers that everyday people don't really understand the concept of molarity in the first place, and then you're talking about numbers that are so incredibly small that it's difficult to comprehend. And so how do we talk about acidity or a concentration of hydrogen ions in a reasonable way, in a number that's more reasonable for humans to understand? And pH is the answer. pH is basically taking the concentration of the H plus and turning it into a logarithmic scale. So for example, if you have a concentration of 1 times 10 to the negative fourth molar H plus ions in solution, and you take the log of that, what you're going to get is a number that's negative 4. Well, negative numbers, just like small numbers, are not necessarily easy to comprehend. And so what we've done is then take a negative sign and just multiply it by a negative sign to flip the sign. So if something has a concentration of 1 times 10 to the negative fourth, if you take the negative log of that, you get a pH of 4. So we've taken numbers that are really, really small. We've turned them into smaller numbers that are between 0 and 14, because that's what the pH scale measures, is between 0 and 14. So I ask you this question: what is the pH when H plus equals OH? Well, in the last lesson, we talked about how the concentration of H plus and OH minus are both 1 times 10 to the negative seventh in just standard water. So I take the negative log of 1 times 10 to the negative seventh, and the pH equals 7. If you have any familiarity with the pH scale, you know that 7 is the middle of the pH scale. We consider that pH to be neutral. Anything less than 7, we call it acidic, and anything greater than 7, we call it basic, but 7 is right in the middle, neutral. Now, what is the maximum pH? Now, let's assume you've got water at equilibrium, and you pack in all the H plus that you can get to up to a molarity of 1.0. That's the maximum molarity that concentration of H plus can get to, at least in our purposes. You can have higher than 1.0 molar H plus, but in this class, 1.0 will be the maximum concentration that we talk about or use. And so let's say that you have a concentration of 1.0 molar H plus, and we know that the concentration of the OH minus times the concentration of H plus equals 1 times 10 to the negative 14th, right? kW of water. So if we solve for OH minus concentration, we have, well, 1 times 10 to the negative 14th. So if we take the concentration of 1.0 molar for the H plus concentration, and we take the negative log of 1.0 molar, well, the negative log of 1 is 0. So actually what I did here is I've calculated the minimum, not the maximum. The minimum is when we have all H plus at 1.0 molar and the OH concentration is so small that it's essentially 0. So on the other hand, if I have a maximum pH, I increase the concentration of the OH minus to 1.0. Once again, that's the maximum molarity that we're going to deal with in this class. And so the H plus concentration gets so small that it's 1 times 10 to the negative 14th. And if you take the negative log of 1 times 10 to the negative 14th, well, you get 14. So that would be the maximum pH. So now we've established how you can have a maximum pH of 14 and a minimum pH of 0. So here's a look at our pH scale. As we talked about, water, neutral, 7. Anything less than that is on the acidic side, going all the way down to 0, and anything greater than that on the basic side, going up to 14, is basic, or another word for basic is called alkaline. And you've got various substances kind of along the pH scale, just to give you some reference points. For example, stomach acid is about 1 pH. Lemon, citric acid is about 2 pH, vinegar 3. You get the idea. Some things on the basic side, such as baking soda at about 9, bleach at about 13, and drain cleaner, which is the most basic thing that you could possibly buy at the store, at about 14. So the pH scale represents a logarithmic scale where every number is times 10 different than the one next to it. So for example, you have a tomato. How many times more acidic is vinegar than tomato? You would say 10 times, because 3 is 10 times more acidic than 4 is in the logarithmic pH scale. So each time you move, that's a factor of multiple of 10. So times 10 times 10 times 10. So going to the left, you're getting 10 times more acidic, and going to the right, you're getting 10 times less acidic or more basic. As you go to the right, you increase the amount of OH minus in solution, and you decrease the amount of H plus in solution, and so your pH is going up, but your acidity is actually going down by a factor of 10 times. That's an important observation of the pH scale, because oftentimes if a student sees two numbers that are different in pH, they'll say, oh, 7, that's just 2 times greater in pH than 5, or it's 2 steps away, but they don't really understand that it's actually 10 times 10 or 100 times different. You might be asking yourself, what about OH? Why are we always talking about pH? What about OH? If OH is in solution, shouldn't we be able to calculate the concentration of it? And the answer is yes. But it's oftentimes confusing to have both a pH and a pOH of a substance, and so we kind of stick to just pH. I know acid gets all the credit, but what about the base? I understand. But if pH can measure the H+ concentration, then pOH should be able to measure the OH- concentration, and it can. And so you can use the Kw expression, and if you know the concentration of H+, you can solve for the concentration of OH-, and then take the negative log of OH-, and you get the pOH. But there's also an easier way to do this, because in any solution, if you take the pH and the pOH and add them together, they always equal 14. And so if you know the pH, say, is 4, then you just subtract from 14, and you can find the pOH is 10. So there's 2 ways to do that. You could solve for the OH- concentration using the Kw expression, or you could simply just take the pH and subtract from 14 to find the pOH. So we're going to finish up this video lesson taking a look at all the equations all in one spot. We've already talked about the Kw expression, which is used to calculate the concentration of OH- if we know the H+, or if we know the H+, we can calculate the OH-. We also talked about this one on the last slide, where the pH and the pOH of a substance added together always equals 14. Now these two are kind of inverse of each other. The pH is equal to the negative log of the H+. So if you know the H+ concentration, you take the negative log to find the pH. But what if you have the pH and you're trying to find the H+ concentration? How do you work that backwards? Well, to find the H+ concentration, you do 10 to the negative pH power. So you know the pH is 4, you take 10 to the negative 4th power, that's the concentration of the H+. So those are inverse of one another. If you know one, you can solve for the other, just using a little bit of algebra rearrangement. Same with pOH. If you know the OH concentration, take the negative log of it to find the pOH, or if you know the pOH, 10 to the negative pOH power equals OH-. And so all of these, and in fact, sometimes you use multiples of these in order to solve some word problems that we're going to tackle in class at another date and time, but you need to be able to manipulate any of these to be able to solve for the unknown. And so these two kind of just hang out at the top. These are just kind of there. I like to refer to these two as linking equations because they're the only 2 ways that you can link pH and pOH, or OH- and H+ concentration. Use them if you need them, but these ones are often used in collaboration with each other. So sometimes maybe you have the OH- concentration and you're trying to find the pH. You can take the OH- concentration and find the pOH and then subtract it from 14 to find the pH. Or an alternate way is you've got the OH- concentration. You can divide 1 times 10 to the negative 14th by the OH to find the H+, and then find the negative log of that to find the pH. And so there's multiple ways to solve the same problem. It just depends on how comfortable you are with working with this formula, pH plus pOH, or this one, which has the Kw expression. Either way, you're going to get the same answer. Well, let's finish up here doing a couple of these practice problems using those formulas I just showed you. First thing we're going to do is we're going to calculate the H+ concentration if we know that the pH is 1.86. Now, it's important to note that when it comes to pHs, significant figures only count after the decimal for reasons that are more complicated than I care to explain right now. Significant figures for pHs only count after the decimal, so this number only has 2 significant figures, even though it has 3 digits. So when I round my answer, it should reflect the same number of significant figures as the pH, which is 2. So I take 10 to the negative 1.86 power, and I get an answer of 0.0138. But I only want to round that to 2 significant figures, so it's 0.014 molar. Now that's the molarity. Next, I need to calculate the pOH. Well, the pOH is simply just taking the pH and subtracting from 14, because as you know, pH plus pOH equals 14. So if I take 14 minus 1.86, I get an answer of 12.14. Finally, I want to calculate the OH concentration. And if I just calculated the pOH and the one just above, then all I need to do is take 10 to the negative 12.14 power, and I get 7.2 times 10 to the negative 13. And that's to 2 significant figures. Make sure you label that one molarity because that's a concentration. Well, that takes care of this video lesson. Thanks for watching.